In this video, we present our method for providing pilots with additional display information concerning the state of flight automation. Our research goals are focused on surfacing behavior-shaping constraints in cyber-physical human systems. While solutions to this problem are applicable to a multitude of domains which utilize automation systems, we will focus on the augmented flight display we have created for use in our pilot-in-the-loop flight tests. The standard flight display provides little information concerning the state of automation. A variety of real-world failures, such as American Airlines 4184, Scandinavian Airlines 751, and Air France 447, have informed our work. A recurring theme in these incidents is a lack of transparency between the pilot and aircraft behavior or automation compensation. Situations arise where the pilot may misunderstand automation actions, or regain control of the aircraft in an unstable state. For example, in Scandinavian Airlines Flight 751, the pilot directed a decrease in throttle due to unexplained engine surges. However, the automatic throttle control subsequently increased the throttle due to an increase in altitude. This was not, however, a failure in automation. The system responded exactly as it should given the situation. There was an opacity between the pilot and automation state that contributed to the incident. In a 1990 paper on automation control, D.A. Norman states, quote, "The problem is not the presence of automation, but rather its inappropriate design. Operations under normal operating conditions are performed appropriately, but there is inadequate feedback and interaction with the humans who must control the overall conduct of the task." End quote. Our project utilizes the Flight Envelope Protection, or FEP system described in Teclis et al. And Chongvazal et al. This system relies upon the quantitative definition of loss of control proposed in Wilburn and Foster. This definition utilizes a set of 5 two-dimensional envelopes relating to flight parameters that account for aircraft flight dynamics and control use. We believe the vocabulary of limits and safety envelopes lends itself to easy integration into the pilot's model of the aircraft. We have implemented our interface at the Illinois Simulator Laboratory. The flight simulator is based on a Frasca 142 cockpit, and the projected display is driven by a cluster of PCs running X-Plane. In the cockpit, the instrument display is replaced by a digital display. For this project, the display was constructed in Unity. The conventional flight display indicates the spatial orientation and velocity of the aircraft. We supplement this with the addition of indicators showing angle of attack, side slip, and G-load. All of the basic instruments, as well as our novel indicators, are augmented with markers which display FEP-derived limits. For each of these critical flight parameters, we display hard and soft limits. We see here the additional components for roll. As we increase the angle of roll, we near the soft limit. As this limit is exceeded, the perpendicular hard limit line turns red. This display indicates safe operational limits in terms of flight parameters. Our additional interface panel, to the right of the primary display, shows FEP-derived limits as they directly relate to pilot input. For each of the control inputs, we present behavior-shaping constraints in the form of dynamic envelopes. These envelopes serve as salient visual boundaries which constrain safe use of the control column, throttle, and pedals. This display represents an indication of the available control authority and/or suggested control inputs for safe operation of the aircraft, and it accounts for both pilot's intent via input and aircraft safety through envelope presentation. We will focus on the main display box, which shows both pitch and roll. We support 2 separate modes, flight protection on and flight protection off. In both modes, the display indicates the changing boundaries of the envelope. When the system is on and armed, any excursion of an envelope activates the system, modifying pilot input to maintain aircraft control. A blue and green marker indicate pilot input and automation input, respectively. In this scenario, the green automation input is currently controlling the aircraft, while the blue indicator shows the pilot's directed input. We also support deactivating automation control in the FEP off mode. With no automation input, the pilot is able to steer the plane beyond envelopes of safety, but a visual annunciation alerts that loss of control may be imminent. Our system presents a more holistic understanding of aircraft state by augmenting known flight indicators with information about automation state. By increasing pilot situational awareness, we hope to allow them to more fully utilize their expert knowledge and improve overall performance.